Hello everyone, it is I, Gregory. Today we're doing something really cool. We are going to implement a disease model as a set of differential equations on the computer in Python, and we are going to modify it to simulate a zombie apocalypse situation. Really good. I hope you enjoyed this video. Please subscribe. I'm trying to beat the guys at the geology department. Hi. Grrr. So let's jump into it. First of all, math. Make America think harder. #gang gang. And then mathematics. Alright, so say you have a population of some size n. We'll keep this n fixed. Our population consists of susceptible people, infected people, and recovered people. And we'll define some transition rates between the different states in the population. For instance, we'll have some, at every time t, we'll have a number of susceptibles. Susceptible people can get infected. So there are s times I pairs of susceptible infected people. And we'll say that the transition rate, or the chance for the infected people to actually infect the susceptibles, is beta, and this will happen at every time step delta t. So there we have our full first equation, and these will not just disappear, they will move over to the infected group. So here we'll have the exact same term but with different sign. So I hope you understand that. And this is not susceptible, these are infected. And I'll just write up the last equation and I'll go through it once again. The last one is covered. And from here we have some chance nu for the infected people to recover, and this also happens for every time step delta t. So we have three groups. At some advancement in time, we move from our current number of susceptible people, and some of the susceptible people become infected, so this increases, right? So we go from here and over to this group. Similarly, we have some chance or some rate of transition from the infected group and over to the recovered group. And as you can see, since we only move from susceptible to infected to recovered, there's no way for anyone to ever get back to the susceptible group. So this is a somewhat realistic model when you're modeling the normal flu or something like that. You don't really get infected with the same virus twice. There will be a mutation of the virus when the next flu season arrives. And what we can do is, as you probably can see, if we move the current value over to the left-hand side by subtracting it from both sides and divide by delta t, we get the definition of the derivative, like so. So the first equation becomes this. Oops, we divided by delta t. There we go. So each of these equations become differential equations, which is what we want. So this first one, we'll write it in the shorthand form, equals minus beta s times I, and the second one becomes I derivative equals plus beta si minus nu I, and the last one is derivative of r, which equals ui. And that's it. That's our first model. So let's implement it. Okay, so here we go. First, we are going to open a new file, save it as SAR. That's the name of our model. It's going to be a Python file. The first thing we'll start to do, we're just going to write a short comment of what this thing is all about. So it's an SAR, this is model. We have the derivative of s, which equals minus beta times s times I. And we have I derivatives equals beta times s times I minus nu times I, like so. And the, just as we just wrote up, times nu times I there, that should be it. And what we also need is we need some sort of solver. So what this file is going to contain is a definition of the equations, the actual problem. It makes sense to write a class that is a general differential equation solver. So let's go ahead and open up a new file. We call this the ODE solver.py. We are going to import a numerical Python, of course, because we always need it, and start right away on the class ODE solver. Yeah, and this is going to be a superclass, so we can implement all kinds of types of solver because there's a whole bunch. And right now all we need is an initializer and a constructor. It's going to take in the model or the problem, which we will define afterwards in this other file there, SAR. And we are going to, the main method of this class is the advance method, which advances our problem one time step. So this is advance solution one time step. Oops, there we go. Okay, and we will implement this in a subclass. So this will be the parent class, all right? So it's going to raise a not implemented error if you try to call this thing. But we need some other stuff. For all sets of differential equations, we need some initial conditions. So we need a method that sets initial conditions. And we'll call that U is our differential equations, all right? So U0 is the initial conditions. Because we have a set of equations, we need this method to be able to manage that problem. So if we only get one number as initial conditions, if this is an int or float, then we want to treat it as that we just have one equation, right? So this is what we call a scalar ODE, and the number of equations will be 1. And we'll make sure that this is a float. Yeah, like so. There you go. And else we'll have a system of equations, and UO will be an array using this numpy method U0, and self.number of equations will be, what makes this the same value, there you go. Shorthand UO.size. Alright, hope you're all catching on so far. And we'll store this within the class. There you go, that should be it. And then we already have the advance method up here, but we need a method that actually solves the entire problem and calls this methods repeatedly, and that can be in this superclass, this parent class. And just to make sure we know what we're doing, we'll write a little note. Any classes inheriting from this superclass must implement advance method. Alright, save that. And we go all down here, and then we'll need to implement the solve method. So what's this going to take as argument is some time points, because we will solve every equation for a bunch of time points, and this will also decide what precision we'll be using. So time points is one of the arguments, and these time points we'll just call t, and they should be as array time points, like so. And the number of time points is n. They'll be the size of this thing. Yeah. And we will make an empty array for the solutions, or the solution at every time point, the u's, which will be MP. So they'll just be empty now, dot zeros. There'll be the size of our t array, long, and the width, or well, however you think about it, will be the number of equations, which we figured out up above here. So there we have everything we need. And now we assume that the starting point, t0, corresponds to the initial condition. So the first points here, the entire width of it, with the first time point of our U array, the solution array, will be U0. Yes. And now we need to integrate, because these are differential equations. So because we have a derivative on the left hand side, let me just scroll up to, or change files here. We need to integrate these, and an integration that's really just multiplying by a time interval that's very, very small. I don't know if you remember the definition of interval, but that's really the area under a graph, right? So that's what we want to do for every small time step. So for I in range of the length of our time array, the n time steps, n minus 1, because we already used one, alright? We are going... Okay, we probably need that one, so I'm just going to save it. And then self.ui plus 1. This is why we have n minus 1 here, because we are computing the next step. Alright? We are going to call the advance method. Not yet implemented. Sorry if this is a little bit confusing right now, but you'll see in a minute what I am going towards. And we are going to return this entire thing. That's everything we need. The u's, which are the solutions, whoops, all the way to I plus 2, and the t's. So, whoops. Yeah, I think that should make sense. Good. Okay, and now we'll write a subclass. Let me just scroll up, here we go. And we'll implement the most simple solver that exists for an integrator, which is really what this is, and for solving simple ordinary differential equation, which is the forward Euler methods. There we go. So it inherits from our guy above here, and the only thing we need to implement is the advance method. So what it does, we have solutions, we have a function, we have some time step and the entire time array. So we're just going to get all these like so, and we need the size of a tiny time step because we're going to use it when we integrate. And for all the equations, that's what the colon means, at this particular step I, we want to multiply by our tiny time step our function. That's what the integration is. So, and the function takes in arguments. Yeah, we haven't really implemented this yet. Yeah, so now we're incrementing, we're advancing in time. This is the solution we're currently at, and we want to keep going. Yeah, I think that makes sense. Because if we go back to our model now, what do we need? We need a numerical Python library. I think that will do for now. And this is also going to be a class. Susceptible, infected, recovered. And this is just going to hold the problem. So we need a transition rate for new that defines how we go from infected to recovered. We have beta, which defines how we go from susceptible to infected. And we also need the initial conditions. Yeah. Good. And yeah, we can write some little commentary on what the things are. New, beta, they are parameters in the ODE system. And the S0, the I0, whoops, I0 and R0 are initial values. Alright, there we go. And just to make this a little bit robust, I think it would be cool if the new and the beta, the transition rates, can vary with time. So how we'll do this is we'll check if they're a number or if they're callables, if they're functions. I think this works. Yeah, so if we have an instance, new first, it's a float or an integer. So is number. Whoops. Oh, can I type? There you go. But in order to make these callable in time, I think we cannot just set them equal like so, because if we want to evaluate them at some time point, if they were callables, okay, so this is what I'm thinking. Else if callable new, then it's some sort of function, right? But here you see that that line and this line is exactly the same. So in order to make this work, if it's only a number, we will make it a function. So yeah, this is a lambda one-liner function, so for any t you put in, you get the same new out. Yeah. And we'll do the same for beta. Yeah, good. So there you go. It's also picked up the there. Oh, just remove that. Yeah. And we also need to store the initial conditions. Initial conditions equals an array S0, I0, R0. There we go. And the only thing we need to do with this class is to be able to call these functions at some u and t. So the u here that we put into this call method will be where we're currently at this t. Yeah. So from this u we will be able to get the SI and R, like so. And the only thing that this method is supposed to do is to evaluate the function at the current time step. So we'll return that as array. There we go. Okay, and then we need the stuff up here. Minus beta times s times I. Minus beta times, the beta should now be time dependent, self.beta t times s times I. And the s and I we have from up here, right? And the next thing, so this is susceptibles. The next is beta times s times I minus nu times I. So self.beta at time t times s times I minus self.nu t times I. These are the infected. We also need a comma. And the last one is nu times I. So self.nu time t times I. And these are the recovered. There. I think that should do it. And as you can see now, I get this little green wiggly lines because we aren't really using the R value. So the Python way to deal with that is to just write an underscore instead. There. And now it's not complaining anymore. Okay. So now you probably get this. So this f that we stored here in the constructor of the class is evaluated here. So here we have the current solution, and then we insert this thing and the time step we're currently at into the problem definition of the problem, which is stored here, and that's going to be this guy. All right. So now we want to use our ODE solver. From ODE solver import what's it called? Forward Euler, yeah. And we would probably also like to plot something, so I'm going to import matplotlib, import pyplot as plt. And then we go down to the bottom. So here we go. This stuff is classes and stuff. So this, if we would like to build on this in the future, we should make it so that we could import it without it running everything. So we'll do this little neat trick. So if we try to run just this script now, this code will run. That's what this incantation means. But if we want to import this class and, I don't know, inherit from it and implement something more, then we can do that as well without this stuff being called. We'll start by defining the SAR model, SAR, and our new transition rate from infected to recovered. We're going to say that's 10%. And the beta, that's the transition from susceptible to infected, or the probability for an infected person infecting, or sick person infecting a susceptible person. We'll put this very, very low, 0, 0, 5, yeah. And we'll have 1500 people and just 1 infected person and 0 recovered persons. So, and we'll need a solver, and that will be our forward Euler, which needs a problem there. And we need to set initial conditions. So what we do? Yeah, SAR.initial conditions, and that should be it. And now we need to define some time steps. So I think it makes sense to pretend that these are days. Typical flu seasons, 2 months or something, so from 0 to 60 days, and we'll have a resolution at 1000. Our U and our T, and now we are actually going to solve it. So the solver.solve all the time steps. Yeah, I wrote both steps and points. Yeah, whatever, it's fine, works. Okay, what I want to do is just try to run it and see if it works. So here we have the SAR Python. Oh, we need to save it first. There. No errors! What the hell? Never happened to me before. So good. So we want to plot something just to see something. So 0, that's our susceptible, and we have Q1, that's our infected, and we have our, just scroll up a little, TU 2, and that's our recovered. Yeah, I think that's correct. And we want a legend to see our labels, and we want to show this stuff. Alright. I have iBooks open. That's how cool am I? Okay, let's see. Here we go. Look at that. So here we see the susceptibles. They start at 1500, and we have 1 infected guy. So we see that people get more and more infected, and it reaches a peak here, and at the same time the susceptibles fall, as one would assume. And oh, Risi overed, they keep going. So yeah, that's cool. And now we can play around with this thing. Say that it's very easy to get infected. We do this and run it again. Whoops. Oh yeah, it's probably too large, so we get some, what was the error? Overflow. Wow. Okay, let's try it now. Oh yeah, okay, that didn't work. Okay, is it entirely broken? No, no. There you go. Still fine. But say we want to model that during the course of this flu season that people are noticed by the government or authorities or someone that they should wash their hands. So the rate of infection goes down. So first we start at the same value that we had, and then, so that's if we're in the first 10 days, say, right? Yeah, and after that we go down to 1/5 of the transition rate, and we do this. So this was the reason for us implementing this callable little logic here. Yeah, think I did it correctly, so let's try. Yeah, there you go. Sorry, I just need to fix my typo. Covered. There we go. Called again. Here we are. So here you see this little kink at the curves. So this is where people start washing their hands. And we see that we don't get that big peak up here that we saw the last time. Yeah, so that was pretty cool. This was part 1 of the SAR modeling. Next episode coming up, zombies. I will put the work I've done here up to GitHub and leave a link down below so you can look at it. So subscribe to get noticed when the next video is up.